Hello guys, welcome to another tutorial series. Today we shall be considering an aspect of information retrieval and text mining. Information retrieval and text mining. As you know, our approach is to use example to illustrate the module that we have to discuss today. And the module we'll be talking is the probabilistic model of information retrieval. So let's look at the example that we want to consider. I'll just put that up quickly. So there is the example that we want to consider. So we're going to walk through this example together, and I would like you to pay attention to this very carefully. Now, here we have two documents here. As you can see, we have two documents. These are document collection, so we can have as many documents as possible, but we're just using these two for explanation purpose. So we have a document collection. Alright, so document collection is just it could be whatever we consider as a document collection. It could be a file. Each document can be a file, so when you have more than one, then that's a collection. So we have file 1, file 2, file 3. That could be, it could be emails. So you have email from a bank, email from the health institution, or it could be email from different people, email 1, email 2, matter. So your document collection depends on what you want to refer as a document. So here we're just considering that we have, like, say, two files, and in the first file, which is the document 1, we have in it these words. So these are the words that we have in document 1. In document 1, we have this work, we have Xerox, we have report, we have A, we have profit, and on like that. So, and in document 2, we have listen, narrows, quarter loss, and this. So each of them is the word that we have in the associated document. So, but this for document 2. Now, what we want to do is, suppose we have a query. Somebody asks us that, gives us a query. For example, if the query is revenue and down, the content of the query is this: which of these two documents closely match this query? I want us to understand that. So I have a query, revenue and down. The content of the query is revenue, and just like you go to Google, you go to search and you search revenue, and you type revenue down, and the Google's database has millions of documents. So let's just limit it at 2. And in the first document you have this, In the second document you have this. So which one should be returned first? Which one should be in high ranking? That's the subject of this tutorial group, this tutorial, and that's what we're using this example to illustrate. So there are a number of techniques for doing this. There's binary model, there's vector space model, and we have the probabilistic model. So today we just want to see how we can use probabilistic model, probabilistic ranking principle, to be able to return result for this query. Alright, so here is the model. Here is the formula for the model. So the probability of Q, our query, given document collection is the product of the words, W is the words that are contained in the query. In this case, our words revenue, and our words are revenue and down. So the words we have here, so in this case W is equal to revenue, then down. Okay, so that is what we have in the word. So separated with that, so I can separate it this way so that you know there are different words not together, so each one is tokenized. We tokenize them to a single gram, called a unigram. The single gram. Okay, now so we look at the words. So the words that are part of the query. Now you need to pay attention to this, because there are words in the document collection. When I talk about document collection, I'm talking about these two. There are some words in the document collection that are not contained in the given query. So specifically, this formula will be applied to the words that are in the query. So we need to get that very right. That has to be taken correctly. The words that are in the query. Okay, very important. Strictly in the query. Now, if I had another word to this revenue now, and I had reports to this query, and I have revenue done report, then I have to include report in my calculation, my formula. So this is the formula, but we're going to break this formula down, then we see how it came to be. So let's look at it briefly. So this is the probability of the word in the modal mixture, that is MC. This is probability of the word in the document model. MC is the collection of the document collection, the entire document. MD is a particular document, the document model. So let's look at it. Why this this symbol gamma is a constant. Here it is given as 1/2. So let's quickly look at each of these components before we use the formula. So I go back to previous explanation on this. So here is where we have an explanation on this model. So this is it, just in summary. Now we infer a language model for each document. Estimate the probability of generating the query according to each of these models. So we want to estimate the probability of generating the query according to each of these models. So PQ of MD is the probability of Q, the query, given these model. So given the model, so rank the document according to these probabilities, and that is what we want to achieve. We want to rank the document. For example, we go to Google and Google returns a million documents. If what you actually need is on number 150,000 or number 500,000, it is useless to you. So you want the document to be ranked, to be sorted in a way that what you need is what you see in the very first two returns, first page. So usually a unigram estimate of words is used, like I said the other time, each word, not bigram. Bigram is when you are like putting when you're like to be, like for example, this is Shakespeare, this is a bigram. Or when you bigram, when you have two words together that are separated by a hyphen, there are a number of them in the English words. So but here we say usually we use a unigram, that is words that are not combined with other words. Okay, so collections are integral part of language model. So how do we estimate the probability of the query given the document model? And so this is it. So this is query generation probability. So here, the probability of producing the query given the language model of document D under the unigram association is this. So this is the formula we're using. Okay, now, so the probability of the query given the language model of the document is the product of all the words, the product of the probability of all the words that are contained in the query. So like I said the other time, I said this is the words that we have in our query, revenue and down. So we would look at the probability of revenue, in the document. We look at the probability of down in the document, then we now multiply it. That is what this symbol means. The product sum of the probability of each word in the query as contained in the document. So that's what you have here. So now, what do we use as our probability? As you know that the probability is the number of items in the collection over the total number of collection. So here, that is here, the probability of a word in the document model is the TL of the word in the document, that is the term frequency. The term frequency of the word in the document. The term frequency talks about the frequency of term, the number of times that a term occurs in a document. I hope that is clear. Let me quickly explain what the TF means. The term frequency. For example, in this particular document, if you take the word Xerox, you will see that in document 1, Xerox appears only once. So the frequency of Xerox, the time frequency of Xerox in document 1 is just 1. If you look at Lucent, the time frequency of Lucent in document 2 is just 1 because it occurs only once. But if you take, for example, document 1 and document 2 together as a single document, the time frequency of revenue in the entire document, in these two documents, is 2 because it occurs twice. Okay? I hope that is clear. I believe that should be clear. And which other document, which other word occurs twice there? Listen, narrow, scatter. But, we see but here. You see that but also occurs twice. So the time frequency of but in the entire document is 2. But if it is in just document 1, the time frequency of but is just 1. I hope you understand those little differences. They are very important. So, and that's what we are trying to say here. So, MD is the language model of the document. TFW is the raw time frequency of word in the document D that we're considering. While LD is the total number of tokens in document D. And so that is another important one. When we say the total number of tokens, we mean the total number of unique words in the document. Because you can have a document where we have repetition of some words. So you will just take one occurrence of that as a count. That is very, 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 very important for us. So the total number of tokens means unique in the document, unique tokens. So for instance, using this to explain, if I want to get the total number of tokens, in document 1, so I will take Xerox 1, report, A, profit, but revenue is down. So I have 1, 2, 3, 4, 5, 6, 7, 8 in document 1. If I want to take for document 2 only, I will have Lucent, narrow, scatter. That is 1, 2, 3, 4, 5, 6, 7, 8. Now, but if they ask me that I should get the total number of tokens in these two documents, you can probably do that as an exercise and pause this before I give you the answer. The total number of tokens in document 1 and document 2. Just do that as an exercise. You can pause this video and get your answer. Now, I believe you have your answer now. So, the total number of tokens in these two documents, that is document 1 and document 2 together, let's do it. So you have 1, 2, 3, 4, 5, 6, 7, 8. Then 9, 10, 11, 12. But when you get here, you won't count this again because it's already counted here. So you will mean that when you get here, you won't count this again because it's already counted here. So when you get here, this is 13, 14. So you have 14 total number of tokens. I hope that is clear. It's very, very important to get that clear. So that's total number of tokens in the document. So that is what we have for probability of query in the document. Now let's look at, we won't be considering the smoothing part now, but let's look at this, the probability of the words in the document collection. I've explained that in a way, but just to see, a non-occurring term is possible, okay, but no more likely than would be expected by chance in the collection. So what we're saying is that there are some terms that are not occurring. So if the term frequency of word in the document equals to 0, Alright, then the probability of words of NC equals to CFW of T. Now this is what we're trying to say here. There are some times that we have insufficient data, okay, and what you mean is, if you want to get the probability of a query in a particular document, once that query, the word of the query is not occurring in that document, then nothing will be returned. That's what this is trying to say, zero probability. That may not wish to assign the probability of a zero to a document that is missing one or more of the query terms. We don't want to do that. Give strict conjunctive semantics. Need to smoothen probability. Many approaches to smoothing probability to deal with this problem, adding one or half of this. But this is a general approach. So do you understand what we're trying to say here? Now let me explain what this means. We want to avoid the zero probability, because look, for instance, there in this document, let's say the query is let's say the query is let's say the query, we are asked to calculate the query, the probability of the query in document 1, and let's say the query contains lucent. So by the time you say probability of lucent in document 1, now we are just considering document 1 alone. By the time because lucent does not appear in document 1, then your TF will be 0. Your term frequency that we explain here will be 0. And once this is 0, everything will become 0. So eventually your probability for that particular document will be 0, which is generally not the best for us. We want a ranking even when the particular term does not appear. We still want some value, some weight given to that particular query. So that is why we say that is either you do smoothing, but in this tutorial we're not considering smoothing, or you use what they call a mixture model, which we consider generally. So what I'm saying is that, so if it does not occur in that particular document, it probably might occur in the entire document collection. So that's why we use this mixture model. So we say the probability of word in the collection, the mixture model in the document collection. So this is which is CFW over T. The CFW is the raw count of word in the collection, and T is the raw collection size, the total number of tokens in the collection. So you should remember this one is frequency, raw count, while this one is unique. So you need to understand. So that's now what gives back to the mixture model. So simple idea, use a mixture model between the document multinomial and the collection multinomial to be able to solve the problem of zero probability. So you look here, so mixes the probability from the document with the general collection frequency of the word, and correctly setting this constant is important. So we get here into the equation represents the probability that the document that the user had in mind. So that's what that equation is trying to say. So this is general language model, this is individual document model. So let's now go back to our example based on that background information that we have. So this is the formula. So this is the product of this whole thing for each the product sum for each the product of these for each word that are contained in the query. So let's get down to business now, which is very easy for us to do. So we have the solution here, and you can look at it. So given this now, so the probability of the query in document 1. So we take revenue first. You take revenue first. So you go and check in document 1. This is, you are calculating the probability of Q in document 1. So you take revenue, check what is the, so if you look here, we have this is half. So you check, this is products, the probability of words in the document mixture plus the probability of the word in the document model. So the word we are considering now is revenue. So you check what is the probability of revenue in document 1. So what is the term frequency of revenue? It is 1. So that is why you have 1 here. Okay. And what is the total number of tokens in document 1? We already said that is 8. So that's why you have 8 here. So you have this plus, you're just inserting into the formula. Then what is the, we are still considering revenue. What is the probability of revenue in the entire document? The entire document. We are done with this part. We are done with this part, so we are doing this part now. So we have plus. This is the plus. So what is the probability of revenue in the entire document collection? Alright, so revenue occurs twice, so that is why we have 2. The entire document collection is 14, so there was an error in this slide, so this should be 14. And I hope you correct that. This is 14. They made an error here, so this is 14. That is, we are true for revenue. Okay, then product is multiply with the next one, the next word in our query, or next token in our query is down. So we do the same thing. What is the probability of down in document 1? So how many times does it occur? It occurs only 1, so that's why we have 1. Then what is the total number of tokens in document 1? That is 8. So you have 8 here. You have this plus. We're still considering the down, the token down. And you look at what is the probability of down in the entire document collection. You see down occurs only 1. And what is the total number of collection? Total number of tokens in the collection, that is 14. So this should be 14. So replace wherever you see 16 with 14. Okay, it didn't take account that these are duplicated, so you're supposed to remove the duplicate. Now the rest is just this gamma. So this is half. So by the time you remove this is half, this is half. That's why you divide this by 2. And the same thing here, that's why you divide this by 2. You can factor out the half. So that's why you have divided by 2, divided by 2. And you do the calculation. Similarly, for document 2, you do the same calculation. So you take revenue, which is the first token in the query. So in how many times does query revenue occurs in document 2, that is 1/8, total number of tokens in document 2. Then you have your formula plus, again in the total number, so this will generally be the same, 2/14, you divide by 2. And don't forget this multiplication, because we are talking about the products of the probability for each of the words that are contained in the query. So we come here too for down. This is the part for down, because down does not occur in document 2. The probability is down frequency is 0/8, which is 0, but it occurs in the entire document once. This is 1, that is 1/16. And by the time you do this calculation, whichever one is higher, so at the end of the day, document 1 will rank higher than document 2. So thank you very much for listening. Please, if you like this tutorial, please encourage us by giving us a like, and if you don't like it, do also let us know by giving us a dislike. You can add any comment which will help us to improve on our subsequent tutorials. Thank you very much.